Hello and welcome to Sean White's Solar and Energy Storage Podcast. This week, we're going to talk about electricity basics from one of my energy storage classes. We're going to get into voltage, current, power, energy, kilowatt hours, and all kinds of crazy stuff. We're going to even get inside of the heads of Mr. Charles Coulomb and Mr. Henry Ampere. I wonder if they knew each other. I think they're kind of related. Did you know that 1 amp is about 6 times 10 to the 18 electrons passing by in a second? That is a lot in a short amount of time. And did you know that that many electrons, that's 6 times 10 to the 18th electrons, is also called a Coulomb? So a Coulomb of electrons passing by in a second, that's an amp. That's how those guys are related. And did you know that some batteries do charging by Coulomb counting? So it's by counting all those electrons. How can anyone count that high? So for more interesting facts like these, like how fast electricity goes, for instance, listen to Sean's podcasts or go to solarsean.com and sign up for Sean's heat spring classes, or hire him for something else. Or hire him to do a class where you are, as long as it won't kill you from catching some virus. Let's get on with the show. Let's talk about the basics of electricity. So there's a lot of different aspects of electricity, and we're talking energy storage. There's a lot of different things that we're going to get into, so it's good to get a good grasp of this. If you're already a solar expert, this might be something you can skip through quick. And some of the things that are important for us would be energy, which is measured in watt hours or kilowatt hours or megawatt hours or even calories. Then there is power, which is measured in watts or kilowatts or megawatts or gigawatts. Then there are volts or kilovolts, and there are amps, and there are amp hours. And so let's talk about charge. Since some of you will be charging batteries, it's probably a good thing to get familiar with. Central to the idea of energy storage is the idea of charge. Batteries and capacitors actually store charge directly. And when a piece of metal, a conductor, is attached to both sides of them, forming a closed circuit, the charge gets pumped through the wire and generates electric power. By the way, safety note, don't ever short circuit a battery. It will explode. You can short circuit PV modules since they are current limited, but with batteries, you could have a lot of energy in there and you release that all at once and kaboom. So before you close that circuit, make sure there's a load in there so it won't short out. Since charge and electricity in general can be difficult to conceptualize, the analogy of a water system is often used to explain it in a way that we can better understand. Charge in this analogy is the water itself, and something that stores it like a battery can be thought of as a water tank. Generators like wind or water turbines act like pumps in this analogy, except they use spinning magnets to propel charges through a wire at close to the speed of light. And yes, light does travel fast. So light in a vacuum travels at about 186,000 miles per second. That's otherwise known as 300,000 kilometers per second. Light travels at a different speed through water or through the glass in your glasses, and that's why light bends. But when light is traveling past a black hole, it's actually space that bends. Go figure. Sounds like there's a Chuck Norris joke in there somewhere. So light and electricity traveling at this speed can cross the United States in about 1 pulse of a sine wave. So our electricity in the United States is 60 cycles per second, alternating current, which means in 1/60th of a second or 1 cycle, light and electricity can travel all the way across the country. Man, is that fast. But then, if you really want to get super technical, it's not really the electrons that are moving that fast. They move about as fast as a snail, but it's the electrons pushing on the electrons. Say that you had 100 marbles in a hose and you pushed one on one end, it would push the other out of the other end. Electricity is a very generic term for explaining, well, electricity. And if we want to get more specific, we talk about current and voltage and power. So if you don't know what you're talking about, say electricity. Makes it a lot easier, and you would be a lot less likely to mess up. Another thing about this electricity is since it moves so fast, we need to store it. Electricity goes in and out of a solar module just about the speed of light, but electricity gets stored for a long time. So let's talk about early stuff here again. And I know we've completed our history lesson, but let's get a little bit back to it. Let's talk about charge. Charge is what allows electricity to work. We don't talk too much about coulombs when we're dealing with batteries in a practical nature, but let's just talk about it anyway. A coulomb is an amp second. Think of battery capacity oftentimes practically measured in amp hours. So 60 seconds times 60 minutes is 3,600 seconds per hour. So 3,600 coulombs equals 1 amp hour. Amp hours are kind of strange to people that aren't battery freaks. I like to really talk about energy because that's what it is, but coulombs have to do with electron seconds. And so amp hours, which we usually talk about when we're sizing battery systems, especially lead acid battery systems, are rated in amp hours a lot of times. You'll see people talking about lithium battery cells rated in amp hours, but usually lithium energy storage systems are rated in watt hours or kilowatt hours or megawatt hours if you're big time. The symbol for a coulomb is a Q, and we describe coulombs or amp hours as capacity. We talk about the capacity of a battery. But as you can see, volts aren't included in the capacity of a battery. So a battery can have the same capacity, but if it has double the volts, it will have double the energy because capacity times voltage gives us energy. Amp hours times volts equals watt hours. The charge was first discovered in the 19th century by a few different scientists, but the unit was named after Charles Augustin de Coulomb, who studied the forces produced by electric charges in the 18th century. A big capital Q is used to represent charges in equations, but sometimes the little q is used to represent individual charges, especially in diagrams. The amount of a charge a battery carries is called its capacity and can be thought of as the size of the water tank in the water analogy. However, the height of the water tank would be more describing the voltage. Voltage is electrical potential difference. So that means in order to describe voltage, you have to have two things to compare to each other. One good example to look at is a bird on a wire. If you see a bird on a wire, for some reason it's not getting shocked because it's only touching one wire. According to that bird, even though the voltage might be changing positive to negative 60 times per second at thousands of volts, that bird thinks it's at 0 volts all the time, and you're the one changing voltage. But who's right? It's all relative, right, Mr. Einstein? So the analogy that we use for voltage is like the hydraulic analogy for pressure. And if you're looking for that higher pressure, what do? You put your water at a higher level. You put your water up twice as high, you get twice as much storage. This might be helpful when you're designing your first pumped hydro station. Now we have current. Current is a certain amount of electrons per second, and we measure that in amps after Andre Marie Ampere. A lot of times you'll see it spelled out as an ampere or an amp or a capital A. The symbol for current itself, but not the unit, is I for intensity. So an amp is about 6.22 times 10 to the 18 electrons per second. That is a lot of electrons. Therefore, electrons must be really small. So remember, current in the water is sort of like current in electrons. It's the flow. Here's a couple of examples that we have. We have Angel Falls in Venezuela, and that's a high elevation, so that's representing high voltage, but it's a smaller amount of water, so that's representing low current. We have Niagara Falls, which looks high when you're there, but it's way shorter than Angel Falls, and that's showing a lot of flow, a lot of current, but less voltage than Angel Falls. The last time I was at Niagara Falls was for a NABCEP conference in the middle of winter, and this mist was a great snowmaking machine. It was freezing. Now we're going to talk a little bit about resistance. Current is limited by the resistance of a circuit. The units for resistance are ohms, and that symbol for ohms is the omega, which looks like an upside down horseshoe. And so ohms are the units for resistance, and the symbol for resistance is R. But you don't say you had 10 resistances. You will say you had 10 ohms. Thanks to George Ohm. Resistance increases as the wire becomes longer and decreases as the wire becomes thicker. That's why when you go a longer distance, you oftentimes need to make your wire thicker to compensate, or you can increase your voltage. George Ohm first figured out resistance by varying the size of the loads attached to a voltaic pile and measured how the current responded. He realized that high resistance reduces the amount of current that flows through a circuit, and too low of a resistance will create a short circuit that leads to dangerously high currents. With batteries, releasing all that energy at once could cause a fire or damage the batteries. Here's an example of resistance. High resistance is like the thin pipe or squeezing your thumb on a hose, and that reduces the current. Low resistance would be like a big pipe. We could get plenty of flow. Think of that as the size of the wire too. If you had a skinny wire, that's more resistance than a thicker wire. And now, speaking of resistance, we're on to resistors. And if you take an electric circuit class, you can play with these things, and they put resistance on a circuit. Also, loads put resistance on a circuit. Okay, here we have Ohm's law, and one of the things that most people remember is V equals IR. That's Ohm's law, and that means volts equals amps times resistance. V equals IR. We use this equation oftentimes when doing voltage drop calculations. That means how much volts you're going to lose by having a wire that's too skinny or your voltage being too low. With electrical systems, we are usually using grounded systems and connecting things to ground. There's different rules for how high your voltage is and when you have to ground things. And we almost always have to have equipment grounding. So that means all of our equipment that's not supposed to be carrying current is connected to a green or a bare wire and then down to some sort of electrode, which could be a ground rod. Then, in a lot of our systems, we have grounded conductors, which is also known as system grounding. And so that means we have a current carrying conductor that is referenced to ground. And it's only referenced to ground at one place, where you bond together your neutral and your ground wires. So a neutral or a grounded conductor is the current carrying wire, and that wire is usually going to be white. And then your equipment ground and your grounding system and your grounding electrode, those are going to be green or bare wires. And then they're connected to earth through an electrode. An electrode is just a way to plug into earth so you get that earth voltage. There might be a lot of resistance between you and earth, but since you're not running current through earth, or you hopefully aren't because that would not be what you're planning on doing, you're not going to have big differences in voltage from one place in earth to another. Earth is not a good conductor like a piece of metal, but you can measure the voltage of earth. Yeah, I know that sounds kind of weird, but you can, especially wet earth and dry earth. It's not so easy. Voltage drop. If you had some long wires and in one side is a source and another side is a load, something that uses energy, then you're going to have higher voltage at the source than you would at the load. The voltage is always going to be higher where it's coming from than where it's going to. If we have nice thick wires, the voltage drop is going to be less. Also, we're going to talk a little bit about voltage drop versus voltage drop percentage. So if you're losing 4 volts out of 12, you're losing 33% of your voltage and 33% of your power. If you lost 4 volts out of 100, then that would be 4% voltage drop, which is one of the reasons why it's better to have high voltage, because voltage drop percentage determines your power loss. Now let's learn how to measure these things without ending up like Doc from Back to the Future. So we have to talk about electrical safety. Digital multimeter. That clamp right there can measure current through the clamp. Some clamps can only measure AC, and other clamps can measure AC and DC. So if you're going to be working with direct current, make sure you get a clamp that can measure both AC and DC through the clamp. You'll also have a couple of leads that you can put at the bottom of these digital multimeters, and you've got probes that you can touch different things and measure the voltages of, or you can even measure resistances of a wire, such as doing what's called a continuity test. There's all kinds of things that we can do with digital multimeters. They're good to have if you're in the field. Also, if you're going to be using digital multimeter or you're getting near live parts, make sure to wear some gloves. Rubber gloves work better for higher voltages. Electricians also like to use insulated tools. Insulated tools prevent you from shorting things out. If the spark gets big enough, you can vaporize metal. So it's important not to short circuit batteries and utility lines. Another thing about safety is we call it lockout tagout, or sometimes you'll see it abbreviated as LOTO. So if you're working on something, you're not supposed to work on anything live. So you want to lock it in the off position so some do-gooder doesn't come by and turn it on while you're working on it. So always remember, stay safe. Thanks for listening to Sean White's Solar and Energy Storage Podcast. To find out more about Sean's classes, his consulting, all kinds of stuff, go to solarsean.com. Over and out.